Now that we understand how to write our models and specify priors, let's talk about some more steps in model estimation and assessing convergence. So this was described in lecture as well, and there are several new elements that we can specify when fitting an MCMC model. The total number of iterations to run for, the number of burn-in or warm-up iterations, the number of chains to run, and thinning. You specify these in rstanarm as follows, and these are the defaults for each one. So 2,000 iterations, warm up equals iterations divided by 2, and this really just could be any integer. It could be 500, it could be 1,500, really how many burn-in iterations you want. It just has to be less than the total number of iterations. The number of chains to run, 4 is usually sufficient. If you're doing really complicated models, maybe you want to do a little bit more. You can do less if your model is really simple. And then thin equals 1. And thinning is sort of for these in between refresher warm up periods that you have that give you essentially separate out how often you're going to draw to hopefully decrease the autocorrelation necessary. But it's not really recommended you change these unless it's absolutely, well, not absolutely necessary. There are reasons you'll change them, but unless you find a reason to change them, it's usually okay to start with the defaults. So to assess convergence, which is something that we should generally do before we start interpreting our model, STAN provides several tools. One of the really great things about STAN, besides the improvements in the MCMC algorithm it uses, are that it's really, really good about giving you warnings when convergence fails. So we're going to look at two types of convergence warnings here. Ones that are true for any MCMC algorithm, and then there's a couple that are specific to STAN's MCMC algorithm. And we'll also cover how to address them and the tools to check them. In general, if you don't get any warnings, you can be pretty confident that your model converged, but it's usually still good practice to at least check. It doesn't take, it's really not that many extra steps to do it. And there are lots of good tools for doing so. So some of the non-STAN specific convergence failures that you might see, and you'll get warnings for these again if STAN's pretty confident they failed, are low Bayesian fraction of missing information, R hat's too large, effective sample size too low, and markup chains did not converge. So there are somewhat different technical reasons. You might see different warnings as opposed to other ones, but the general idea is the same in each case. The 4 or however many chains you're running, the chains don't seem to have agreed on the correct posterior distribution. So maybe one chain thinks the posterior distribution is covering one space, and then the other 3 think it's in a different space, or all 4 think that the posterior distribution is a little bit different. If that comes up, you're basically in trouble, and your model didn't converge the way you specified it. The bad news is that, as I said, if you get a convergence failure, your model is in some trouble the way you estimated it. The most simple, straightforward solution is to run more iterations. This is better for certain types of warnings than others, especially for effective sample size. This will usually take care of that. For R hats, it may take care of it. Some of the other ones, it may not take care of it. The other options are to change your model. So the good news is that STAN is much better about these issues than older software like JAGS. In standard rstanarm models, these really tend to come up in situations where you're trying to estimate too many random effects, you don't have many observations per cluster, you have predictors that are highly correlated. One thing that happens sometimes is that you have really high, especially in complicated models, you have really high correlations between parameter values. We haven't looked at exactly how to assess this, but that's something that can cause these issues. For more on that, you might want to look into what's called the MCMC pairs plot, but I'm skipping that for time. So here's an example of what some of the warnings will look like. So here I only run 200 iterations of this model, and you see STAN's mad at me. It told me that the largest R hat is 1.19. We have bad effective sample size, and I think there's even more warnings below this that got cut off. But if I simply increase the number of iterations back to the default, these warnings all go away. Hooray! So we could take a closer look at the output. This is sort of just the top of it. It got cut off here, but here's a screenshot of the bottom in particular, which has this section called MC Diagnostics. And so this is for the non-converged model. So this part was cut off. And so what we see here is we have 3 columns for some of our variables. This actually doesn't print out. This isn't all the variables that are printed out. I specifically asked for only these variables. We'll talk a little bit more about that as well. So you see here the R hats are not great. The NFs, which is the ESSs, effective sample size, also not great. So ideally, what you want is to see R hats that are 1. 1.01 is usually okay. 1.02, you're starting to get a little concerned. There's some debate about how big R hats can get before there's a problem. Everyone agrees that pretty much more or less that above 1.10 is problematic. A lot of people think that above 1.05 is problematic, and some even think that above 1.02 or higher is concerning. So for the ESS or the NF, this is the effective sample size. The current thinking is you want these to be at least 100 times the number of chains you've run. So if you have 4 chains, at least 400 each. This may be conservative. In some cases, you can probably get away with less, but it's going to give you warnings for the most part if you're below this. The bottom line is that larger ESS always means more precise estimates. And if you thin, you'll get the ratio of effective sample size to actual sample size will be better, but the trade-off is that you're doing many more iterations because you're throwing so many away. So there's some debate as to whether thinning is good because you're discarding a lot of iterations. Some people think that you should do it because those iterations are correlated with the previous ones. Other people think that's just discarding information that's helpful. In general, I feel my understanding is that you'll typically wind up costing yourself more time with thinning rather than saving time, since you have to run so many more iterations anyway. And it's just going to be better to increase the number of iterations and not thin in a lot of cases. Not every case. There are exceptions, especially if you have to go for a lot of iterations. In that case, then you might want to thin because the discarded iterations don't get stored in memory. So we can also assess the chains graphically, and what we really want to see is just like a noise time series plot. We don't want to see any patterns. We don't want the chains to be staying in the same general location for repeated periods of time. We want them going up and down and just to be totally random as we can get them. And so this is for the non-converged model. So you see on the left the intercept parameter. In some places, it really just stayed in one place for a while. I mean, it still went up and down a little bit, but it's just hanging out kind of in this range up here for a little while and down here. And a lot of the chains are doing this. This is non-converged. The pain parameter is actually a little bit better. It's not great still, but it looks better than the intercept because even in 100 iterations, it's looking like nice and noisy and like it's drawing randomly, but still, this is too few iterations regardless. So here we see the converged version of the model, and these look a lot better. Even these honestly aren't perfect, but they seem to have converged by all the other measures, so we can generally trust them. But even here in the intercept, you see there's a little bit of sort of like, you know, you could sort of trace a line across it here, and that's not ideal, but it's not going to have enough of an impact to really change the results, given what we know from the other diagnostics. But this is a little bit more concerning than over here, where you really can't see any patterns here. Everything's pretty nice and noisy. And the noisier, the better. There are also 2 stand-specific warnings that we should talk about. The first one is called divergent transitions. So these are somewhat common, and they are problematic when you see them. I was taught that even 1 or 2 divergent transitions are at least worth exploring and probably worth trying to fix. It really depends on what you want to invest your time in. You sometimes can try to there are ways to diagnose them and determine that maybe they're not that important, but there are ways to fix them, especially if there are only a few. You can usually get rid of them. The other one is max tree depth. This is less common and conceptually less problematic, although you still have to do something about it if you get the warning. So the sort of intuition behind these is that Stan does this funky thing with how it chooses random parameter values that's based on all these principles in physics, and it's sort of like you can picture a particle rolling down a hill, and it's got some sort of random momentum behind it, and where it stops is the parameter that gets drawn. And so where you can think about divergent transitions are like you're taking steps that are too large. And so if you take too large a step, you might slip and fall, and that's a divergent transition. Max tree depth, on the other hand, is rather than taking too large a step, you're moving too fast. So you could be taking small steps, but you're trying to go really, really fast with them. And this could also cause you to slip and fall. So in theory, you can always slow down enough to slow the max tree depth issues. It just might be annoying to have to slow the algorithm down that much. But you may not be able to solve divergent transitions. It's possible that the hill is just too weird, and that there's no step that's small enough where you won't eventually fall. And if that happens, then the model just isn't something that's solvable by Stan. And if it's not solvable by Stan, there's a good chance it's not solvable by other MCMC software anyway. So to fix these warnings, there are these two tuning parameters that we can set for divergent transitions. There's a DAP delta. And so this has to be between 0 and 1. The default varies. In a lot of Stan programs, it's 0.8. I think in Stan Elmer, it's actually 0.95. So you just have to bump this up a little bit. And if you do, you'll usually be able to get rid of the divergent transitions unless the model is really problematic. To solve max tree depth warnings, you have to increase max tree depth, and they don't actually make this as easy because it's less common in rstanarm models in particular. This is pretty unusual. It may happen from time to time. So you actually have to go into the control argument and then specify control equals list, max tree depth. The default's 15, and you just bump it up a little bit. You don't want to bump it up too high. It's going to slow things down too much. You might want to bump it up to something like 20. So here I bring a DAP delta down way too low, and you see I get this warning. There are 2,200 divergent transitions, and that's really bad. And it also caused problems with all the other warnings too that I did this, and you can see that there. And so we can look at the plots here. So one of the things that happens with divergent transitions is that it actually causes things to level off in some points, and that's really bad. MCMC really doesn't want that. So notice that we're going through 1,000 iterations here. We have these kind of flat lines where it's just the parameter value staying the same for a little while over here too. And if that happens, then yeah, you're in bad shape. You don't want that. So usually in Stan, these options are sufficient for diagnosing and fixing convergence failures. You looked at a couple other options in lecture. I don't want to bog too much down with time for the sake of time. I want to make sure that we get to look at the models and how to use them. So there's some other plots that he showed you that are accessible. There's a plot called the pairs plot, which is good for checking correlations between parameters and divergent transitions. I'm not going to go into them, but something to maybe consider exploring on your own time. Bottom line is, if you're using Stan-based software, if you don't get any warnings, you can be pretty confident. If you get RHAT, ESS, or F fraction of missing information warnings, you can try running more iterations or try changing your model around. You can try to diagnose which parameters are causing the problems with the diagnostics output and the trace plots. And if you get divergent transitions, increase the DAP delta. And if you get max tree depth exceptions, change the max tree depth.